So, hello everyone, today we are going to start the last lecture of week 4, that is application of immobilized enzymes. So, in last few lectures we have discussed about enzyme immobilization. We discussed what is the merits and demerits of confining the enzyme into solid matrix, what are the different techniques for enzyme immobilization, starting from your cross linking to the carrier binding and entrapment. Then what it was observed during immobilization, we are able to improve the stability, we can reuse the enzyme, but at the same time it is affecting the kinetics part. It means it is affecting the value of Km, Vmax as well as the concentration in the bulk. This will decrease to Cs or Ca. So, this keep on decreasing. So, for the first part it says there is change in the catalytic property of enzyme due to entrapment or immobilization, and the second part says there is a mass transfer resistance, and this mass transfer resistance we discuss of two types. One is coming through a stagnant film on the surface. So, this is the film, and second is coming through the diffusion because it is packed in the solids. So, substrate has to diffuse in and product has to diffuse out. So, we discussed the expression for internal mass transfer as well as external mass transfer. Then while discussing intraparticle diffusion, we discussed the Thiele modulus and observable Thiele modulus, which helps us to quickly calculate effectiveness factor in the case of intraparticle diffusion. Further, we discussed simultaneous external and internal mass transfer. So, there we have to first calculate the Biot number to decide whether external mass transfer is significant or not. Then you have to calculate observable Thiele modulus to comment whether internal mass transfer is significant or not. Then we can calculate the effectiveness factor for external mass transfer, effectiveness factor for internal mass transfer, and total effectiveness factor is effectiveness factor for external mass transfer into effectiveness factor for internal mass transfer. Now, considering this kinetics part of applied enzyme catalysis, so what we are going to discuss today, some potential of immobilized enzyme. So, like you can see reaction type, oxidation reduction, group transfer, hydrolysis. Enzyme is, let us say, L amino acid oxidase. This is used for the production of D amino acid. Similarly, if you see in the group transfer, I say dextrasucrase. This is used for the production of dextran. Dextrasucrase used for the production of dextran. In the hydrolysis, you name alpha amylase. This is used for the production of glucose. So, there is cellulose invertase for the production of invert sugar. Similarly, for hydrolysis, you can see the peptine hydrolysis of casein. In addition, for the isomerization, you can use glucose isomerase for the production of fructose at industrial scale. So, this example we will be seeing in the subsequent slide. In addition, there is a lyase reaction. So, we will see one example of aminoacylase in the subsequent slide. So, when we are talking about this industrial application, it refers to used at large scale industrial process. So, one example is production of high fructose syrup from corn starch. So, typically what happens, the sweetness level of fructose is higher as compared to the glucose. So, it is better we keep the syrup rich in fructose rather than glucose. Manufacture of L-amino acid by dissolving racemic mixture and use of penicillin acylase in making semi-synthetic penicillins. The first one, high fructose syrup. As I told, D-glucose, there are certain challenges, cannot fully replace sucrose, this is less sweet, and it crystallizes easily in concentrated solution, which creates hindrance during handling. So, what is the solution for this? You can convert glucose to fructose. Glucose is converted to fructose and enzyme is glucose isomerase to improve sweetness as well as the handling part. You can see this D-glucose is converted to D-fructose. So, this functional group is changed here. So, this aldehyde group is converted to ketone group. So, how it is done? I have listed few steps here. The equilibrium mixture of glucose and fructose is roughly 1:1. The mixture is sweeter than glucose alone, making it ideal for sugar substitution in particularly in soft drink, baked goods and processed food. Fructose enrichment can be done by a chromatographic separation. Further, if needed, one of the sugar can be separated, and glucose isomerase used for isomerization is produced by microbes. One example is Arthobacter and Streptomyces. Disrupting cell to extract glucose isomerase without destroying it is costly. So, glucose isomerase is intracellular enzyme. The enzyme is sensitive to inhibitors and immobilization is preferred for the stability. So, this is the reason we produce glucose isomerase and further it is immobilized during the production of high fructose syrup. Now, how it is immobilized? This is entrapped in collagen or other matrices. So, one option is you entrap in collagen or other solid matrices, other is fix the whole cell to reduce the enzyme loss. So, for this it is prepared from permeabilized or intact cell for reduced mass transfer resistance, and immobilized whole cell system are commonly used for industrial enzyme applications. So, one can directly immobilize the whole cell and other option is one can entrap only the enzyme part. Yeah, so this says you are having this starting raw material is starch that is first converted to glucose through the process of liquefaction and saccharification, and further it goes for isomerization, and this is your final product rich in fructose. The next example is aminoacylase. So, aminoacylase is an enzyme that breaks down N-acyl L-amino acids. It catalyzes hydrolysis, releasing the free amino acid and carboxylic acids. What is the advantage of this? It involves in the protein degradation. Degradation means catabolism. Plays a role in detoxifying foreign compound, acts like xenobiotics, and useful in the synthesis of L-amino acid derivative, which have important application is food technology and medicine. So, you just see this is enzyme aminoacylase and end product is L amino acid and L amino acid and D acylo amino acids. So, it breaks down releasing the free amino acid and carboxylic acid. So, for this a column reactor with immobilized aminoacylase is used to separate desired L amino acid from unhydrolyzed D amino acids. So, for this your substrate or you can say D acyl amino acid is racemized to DL form and recycled to aminoacylase column, and for the immobilization of this enzyme this Sephadex is used because of its high activity, ease of preparation, regeneration capability and long term stability. So, if you see in 1983 the first commercial process using immobilized enzyme via ultrafiltration was reported for conversion of N-acyl D-L-methionine to L-methionine using acylase. So, one can use this ultrafiltration method for the immobilization or the Sephadex for immobilization of acylase. Yeah, it is good to see this comparison here of M aminoacylase. This is the native enzyme and these three are the immobilized using different techniques. So, this is ionic binding, this is covalent binding and this is entrapment. So, for let us compare one parameter here, regeneration. For ionic binding it is possible, you can change the pH or ionic strength to regenerate it. For covalent it is impossible, for entrapment it is impossible. If you see the preparation for ionic binding it is easy and these two are the difficult. Now, it is interesting to compare this kinetic parameter Km. So, Km has increased here and this is slightly decreased, and interestingly the Vmax has increased. Vmax has increased in all three cases. And further you can there is some changes in activation energy as well from 7 6.9 to 7 3.9 and 5.3, and in addition this optimum temperature which was 60 for native enzyme it increased to 72 for in the case of ionic binding, further decreased to 55 for covalent binding and 65 for entrap. So, it says during this different immobilization process there is some intermolecular interaction between enzyme and your solid matrix which is causing certain structural changes in the protein or enzyme and which is reflected in terms of its catalytic activity or its performance. So, optimum pH, let us compare. This native enzyme works best at 7.5 to 8. Immobilized enzyme also have similar optimum pH, with covalent binding allow a slightly broad range 7.5 to 8.5. Optimum temperature, this ionic binding significantly raises the optimum temperature to 72, enhancing its thermal stability. Covalent bonding reduce the stability 55 degree centigrade. So, it says the ionic binding improve thermal stability. Activation energy, covalent binding drastically lowers the activation energy, suggesting more efficient catalysis. And other form you just see the activation energy, it is here it has decreased from 6.9 to 3.9 means catalytic activity will be much more enhanced. Other form have similar or slightly higher activation energy compared to the native. Effect of cofactor. So, all the forms need the cofactor because enzyme cannot work without cofactor. Michaelis-Menten constant. Entrapment, it has slightly better affinity as compared to native because this Km value is slightly decreased, but in other cases ionic binding shows the lower affinity because the Km value has increased from 5.7 to 8.7 and 6.7. Covalent binding gives highest reaction rate, meaning high catalytic activity, which can be correlated with the lower activation energy. You just see the activation energy, it was reduced. Native enzyme is the least, while ionic and entrapment forms show improved activity. Now, if we compare the preparation, the ionic binding is easy, while covalent and entrapped are relatively difficult due to more complex methodology. Now, you can compare the effect of immobilization method on the retention of enzymatic activity. Let us see, compare in terms of performance. So, you can have this different support, and these are the method: entrapment, encapsulation, ionic binding, covalent binding and cross linking, and these are the support which was used for the immobilization. And you just see this enzyme activity in case of entrapment was 526, in case of entrapment in nylon it was 360. You can see it is maximum for this ionic binding using Sephodex, and similar value is also there for the cellulose. For the covalent it is 472, enzyme activity is 39%, but if I go for further different methods like AE cellulose and Sephodex with covalent binding or cross linking, activity has slightly decreased, almost no activity. Interestingly, if you just see Sephodex C50, even through ionic binding the activity has become 0. So, it says the proper immobilization method is very important because it can drastically interfere with enzyme activity. So, here is the you can see the summary. This polyacrylamide, it shows good activity 526 unit. Nylon, it shows moderate activity, and particularly this DEAE cellulose and DEAE Sephodex, it resulted in high observed activity 660 to 680 unit. And interestingly, this CM Sephodex C50, this ionic binding failed completely. This indicates that either binding was unsuccessful or enzyme got inactivated during the immobilization process. Similarly, for these two cases also one can see here that enzyme got denatured or enzyme got inactivated due to the immobilization process. Now, next application we will see medical and analytical biochemistry. So, if you can see here, you have this glass electrode which has a coating of enzyme, that is the urease, which will convert urea to ammonia. So, immobilized enzyme electrode are used for continuous biochemical monitoring of specific substrate. So, here the substrate will be urea. It contains urease that decomposes urea into the ions, and these ions can be detected by different methods like electrochemical methods, and this electrode ultimately enable sensitive detection of a specific biochemical substance, but here the example was urea. One common device which is based on enzyme immobilization is glucometer. So, it utilizes particularly two enzymes, one is glucose oxidase, other is glucose dehydrogenase. So, glucose oxidase converts glucose to gluconic acid and it uses oxygen as electron acceptor, but glucose dehydrogenase uses the cofactors as electron acceptors. So, this enzyme is immobilized on an electrode, and so once glucose is converted to gluconic acid, parallelly oxygen is converted to H2O2, and that can be detected either electrochemical method or the reflectance photometer. And there are many leading brands like One Touch, AccuCheck and Abbott which are producing glucometer in the market. So, here I have compared this. In the case of One Touch, it is using glucose oxidase and glucose dehydrogenase. The glucose oxidase will use oxygen and glucose dehydrogenase will use FAD, flavine adenine dinucleotide. AccuCheck is using glucose dehydrogenase and PQQ, pyroquinone quinone or glucose dehydrogenase FAD, and Abbott freestyle is using glucose oxidase. And you can see the note also, this focus on the fast response and good stability. This glucose dehydrogenase is designed to avoid interference from sugars like maltose. Further, the important advantage here is it does not use oxygen, is not used in this method, and in the case of freestyle or from the Abbott, it is used in continuous glucose monitors, requires biocompatibility and long term action. Further, you can see how the enzymes were immobilized, covalent bonding, entrapment and cross linking, and covalent and adsorption. So, these are the different techniques which has been applied on different surfaces, but it is important that the sensor stability and measurement accuracy should be maintained, means enzyme activity should not get compromised. And many times we have seen these glucometer are reused for n number of cycles as enzymes are immobilized on the surface. One other very good example is ELISA, that is enzyme linked immunosorbent assay. So, this is modern molecular techniques for detection of antigen antibody interaction with the help of enzyme. So, in either antigen or antibody are immobilized on a solid surface. That solid surface, it may be 96 well plate, it says polystyrene well of a microliter plate which allow a specific binding interaction for detection. Now, one can have passive adsorption, covalent binding or affinity binding of either antigen or antibody on the surface. So, passive adsorption is most common, proteins absorb non-covalently on plastic wells. One can use affinity. So, for this biotin streptavidin or protein AG system for the specific immobilization. Because of the immobilization, it provides a stable platform for antigen antibody interactions, and when you are doing this biochemical reaction, we need to go for washing and reuse. So, this stability on the surface of enzyme is very much essential. So, you can see here direct ELISA, indirect ELISA, sandwich ELISA and competitive ELISA. So, ultimately you have to immobilize enzyme, either antigen or antibody on the surface, and that will convert the substrate to the product, and in term you will get the either colorimetric signal or electrochemical signal. So, most of the time in the ELISA we get colorimetric signals. So, with this I will stop here. So, today we discussed the application of immobilized enzyme for different industrial purpose along with medical and analytical purpose as well. So, what we discussed, this selection of immobilization method is very much affecting the enzyme activity in the terms of its performance, in terms of its stability and in terms of its reusability. Thank you so much.